Hello class, this is the video for section 3.5 since I will be traveling to the math conference in Kentucky during that day and I'm unable to be in two places at once. So this class, we're not going to be able to have fun and do stuff together, so you're just going to have to watch me have fun doing math on these videos. So it'll run a little bit differently. But I will start it the same way. Hear, O Israel, the Lord our God, the Lord is one. You shall love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. The second is this: love your neighbor as yourself. There's no commandment greater than these. Okay, this video is going to do that intro and then the preview activities. So you don't have to do these preview activities. I'm going to do them for you because they kind of relate to the rest of the content. So let a equal 27 b equal 4 will now determine several pairs of integers q and r such that 27 equals 4q plus r. For example, if q equals 2 and r is 19, you can obtain 4 times 2 plus 19 equals 27. So the following table is set up for the various values of q. For each q, determine the value of r so that 4q plus r equals 27. So here we have when q was 4, when q was 2, then r was 19. If q was 1, then you've got 23, because 23 plus 1 times 4 is 27. And then you might notice the pattern, it's going to be going down by 4s. So we go to 15, 11, 7, 3, negative 1, negative 5, negative 9, and negative 13. The smallest r is that guy right there. So r equals 3 is the smallest positive 1. And then what are the quotient and remainder when you divide 27 by 4? And so in this case, 27 over 4, you can write as this guy. So 6 plus 3 over 4. Okay. And for you computer science people, the remainder is the thing you get when you do 27 and then this symbol for in different like Python 4 equals 3. Okay, so repeat part 1 using a is negative 17 and b is 5. So the object is to find integers q and r such that negative 17 equals positive 5 times q plus r. Oh, typo. Come on. Okay, 5q plus r. So in this case, 5 times negative 7 is negative 35, and then plus 18 would then be negative 37. So then, so the negative 6 times 5 would be negative 30, so plus 13. And then they're going to go down by 5. So then I get an 8 and a 3 and a negative 2, a negative 7, and a negative 12. So there's my winner with the smallest positive remainder. And so divided by 3. Okay. Now preview activity 2 says let n be a natural number, let a and b be integers. Write the definition of a is congruent to b modulo n, which is written a congruent to b mod n. So that definition is that n, if you combine both unpackings of definitions, you would get there exists an integer k such that a minus b equals nk. Use the definition divides, complete the following. When we write a, we conclude their existence. Oh, I did it 2 parts at once. Okay, it's looking for you to do n divides a minus b, and then here you can then do there exists a k in the integers such that a minus b equals nk. We'll now explore what happens when we multiply several pairs of integers, where the first one is congruent to 3 mod 6, and the second is congruent to 5 modulo 6. We can use set builder notation and the roster method to specify the set A of all integers that are congruent to 3 modulo 6 as follows. So remember, we're doing big set condition, big set condition, and then here's the roster method over here. So use the roster method to specify the set B of all integers that are congruent to 5 modulo 6. So things that are congruent to 5 modulo 6, one of them is going to be 5. Let's go backwards first. So you'll also like -1, -7, dot, dot, dot over here. And then you'll have 11 and 17, and so on and so forth. Notice that 15 is in A and 11 is in B. And then 15 plus 11 is 26. Also know that 26 is 2 modulo 6, and 2 is the smallest positive integer that's congruent to 26 modulo 6. Now choose at least 4 other pairs of integers, a and b, where little a is in big A and little b is in big B. For each pair, calculate a plus b and then determine the smallest positive. So let's make a table here. A, B, A plus B, and then R, which is equivalent to A plus B mod 6. Okay. So let's pick some things from A. They already picked positive 15. 4 more guys. Let's do -9, -3, 3, 9. -9, -3, 3, 9. And let's do, from there, let's do -7, -1, 5, 11. So add them together. I've got like a -12 and a -4 and an 8. The -12 doesn't make any sense. Of course not. -16, +8, +18. Okay. So 8 plus, no, again, 20. 20. So then a plus b mod 6. So then -16. Let's do one of the easiest ones first. This is 2 mod 6. And then -4 is also going to be, the remainder is +2, because you can write -4 equals 6 times -1 plus 2. And then similarly, -16 is 2 away from -18, so +2 there. 20 is also 2 away from 18, so +2 there. These are all 2 larger than a multiple of 6. So look at that, and then prove that for all integers a and b, if a is congruent to 3 mod 6 and b is congruent to 5 mod 6, then a plus b is congruent to 2 mod 6. So let a and b be elements of integers such that a is congruent to 3 mod 6 and b is congruent to 5 mod 6. Then there exists, I'm going to kind of use the shorthand because we're just doing a quick little video here. There exists integers, what do I want to name them? R and S, X and Y. Let's go X and Y. No, K and M. K and M in the integers such that a minus 3 equals 6k and b minus 5 equals 6m. Then a plus b equals 6k plus 3 plus 6m plus 5, and then that's equal to 6 times k. Let me do the algebra slower for you. Equals 6k plus 6m Now notice I've got a 3 plus 5, that's an 8. I'm going to write that 8 as a 6 plus 2. So then that's 6 times k plus n plus 1 plus 2. And so I'm just going fast and loose. I would use better words here if I had more time. But you can also write this as a plus b minus 2 equals 6 times k plus n plus 1, which implies, do I have no more space? All right, implies a plus b is equivalent to 2 mod 6. And then you'd end it, but we're out of space. So that concludes preview activities 1 and 2.